Okay, so I'm going to make a video about U substitution. And so just to start, I'm pointing the camera at the list of antiderivatives to memorize. This is a PDF that's on e-learning, so sorry, I know it's probably shaky to look at on the camera, but we have this list of functions whose antiderivatives we should just know. And so when you get an antiderivative to do, the first thing to hope for is that it's just on the list and then you just know it. But we're going to run into plenty of situations where that's not the case. I'm going to ask you to find antiderivatives of things that are not quite on this list. And so then you're going to need something that we call a technique of integration. Techniques of integration are things that we learn in Calc 2 mostly. They include U substitution, it includes integration by parts, and also other things like partial fractions and what we call trig substitutions, and there's probably more I'm forgetting about right now. But today we're going to talk about U substitutions. So let's do a bunch of examples. So I would say there's basically 4 steps to a U substitution problem. I'll go over these as we do them. So let's get right into it. So I have this function to integrate, and this is not something that's exactly on the list. For our first example, I'm just going to go ahead and tell you what a good idea to make U is. And that's step 1, is to determine U. We're going to do several more examples where we have to decide what to make U, and then I'll get into how you make that choice. But for us, that's step 1. It's already done. So let's move on to completing the substitution. What do I mean by completing the substitution? Well, in the integral that I was given, I'm like the only variable that I see is x. I would like to rewrite this so that the only variable that I see is a u. Completing the substitution involves du, and that's usually a good place to start. To find du, I'm just going to take the derivative, and then whatever this derivative is, I'm going to write dx after it. So the derivative of this is 2x, and then I write a dx after it. Okay. Now that I've done that, let's complete the substitution. So what I'm looking for is I'm looking for ways to replace things, and I don't like seeing the letter x at all. So, yeah. So obviously x squared is what we made u. So if I just replace this x squared with a u, I like that because I don't see the letter x here anymore. Of course, I left myself some space here because I'm kind of not talking about what happened with this 2x yet. I'm going to have to remember I haven't done anything with this yet. So what's left over, I mean, I've taken care of this part, that's right here. What's left over is the 2x I just mentioned and the dx. And for the first time, let me just say I see what's going to happen. I see a 2x dx, and I recognize that here. That's the same as du. So if I just write a du, that takes care of this, and it takes care of this, and we're happy. Everything's there. Everything has been accounted for. And this is a complete substitution. I did not see the letter x here at all. I only see the letter u. Okay? Now, with u substitutions, it's not like a magic bullet, so to speak. You're always going to have to do whatever the new integral is, and that's step 3. So we're always hoping that when we do complete the substitution, when we do complete step 2, that we actually get something that we're able to find the antiderivative of. In this case, we are. In fact, it's on our list. Here's antiderivative of sine x is negative cosine. So this is negative cosine u plus c. Okay, so the calculus part is done. I don't see any more integral signs. It just is what it is. And the last step is to go back to x's, because the original question was involving the letter x. We should give an answer that involves x's and not u's. U is just this made-up thing that we use to get our answer. We don't want to leave u's in our answer. But this is easy enough. U is just x squared. Yeah, so that's that. So we're about to do another one. Let me start talking about step one, because we kind of had, it was on easy mode for the first example we did. We were just told what to make u. Good ideas for what to make u are the inside of a composite function, and that means, I would say, sine of x squared is like a composite function. It's like f of g of x, where f is the sine and g is the x squared. It's typically a good idea, as we did this time, to make u the inside of a composite function. It's also a good idea, and this is kind of the same thing, it's a good idea to make u the denominator of a fraction. And I should just mention that it's not really possible to give you a complete list of things that are a good idea to make u. Sometimes you can have unexpected things that work, but this is just the standard first things to try. So keeping that in mind, let's do the next one. So I see a denominator of a fraction, and that's a good idea to make u. So 3 plus x cubed. So we're good with step one. Now I want to complete the substitution. So I have to look at this integral, and I have to find a way to replace all the x's. I don't want to see any x's when I'm done. The first thing to do is, somehow we know this is going to have to involve du. So I just do the derivative. This is 3x squared. I put a dx on it. Now let me go to make this substitution. So there's usually at least one thing that's obvious, which is that I see u right here. In fact, that's the whole point of why I made u what I made u, is that it's the denominator of this fraction. So I'm pretty sure I'm just going to write u down here instead of 3 plus x cubed. And now maybe, okay, probably a lot of you see how this is going to work out, but let me pretend that I don't. Of course, there's unaccounted for things. I've not accounted for this x squared at all. I also haven't accounted for this dx at all, and I have to put something here to account for those things. Here's a basic trick you can do. Over here, where we found du, I can just solve for dx. I can say dx is as like I'm dividing by 3x squared. Okay, and now watch what I'm going to do. I'm going to have, and this is okay, I'm going to have an intermediate step where I have both x's and u's. And that's okay I know that I'm not done if I have both x's and u's, because ultimately my goal is to not have any x's at all. But it's okay to have an intermediate step with both x's and u's. So here I go. This x squared, I'm not sure what to do with right now. But I can just write x squared. That's the same thing. This dx, I'm just going to write what I got when I just solved for dx. Now that I've written that, I can just do algebra. And miraculously, this x squared that I didn't know what was going to happen with, it has something to cancel. So where am I? I've got this 3 in the bottom. That's like a 1/3, and a 1/3 can come right outside of the integral, like this. And then I've got 1 over u du. And this is an antiderivative that's on our list. We have the integral 1 over x dx is the natural log of the absolute value of x. So this is natural log absolute value of u. And that's okay. So I wasn't really going through, well, I was going through the steps, but I didn't remind you of where we were. We completed the substitution, and just now we did the new integral. Now I just have to go back to x. So finally, I'm just going to replace this u with a 3 plus x cubed, because that's what it was. All right. Let's do another one. I see a composite function here. I see tangent of this thing. I'm going to let u be the inside. That's step 1. I've determined u. Now I want to complete the substitution. That's step 2. Part of that is involving du, so let's go ahead and do that. The derivative of this is just 3, and then I'll write it dx. Now let me go to complete the substitution. And part of this is obvious as usual. The whole reason why I called this u is because I see this here, so I can go ahead and just say this is tan u. And then what am I going to do with the dx? Somehow the dx needs to be accounted for. But I don't just want to write dx because I don't like the letter x. I want to complete the substitution, meaning I only want to see u's, I don't want to see x's. I'm just going to do the same thing again. I can solve for dx. dx is 1/3 du. And instead of dx here, I'm going to write 1/3 du. Okay. And maybe this is overkill to take a whole step for this, but let me go ahead and pull the 1/3 outside of the integral. And then this is something on our list. The antiderivative of tan x is natural log of absolute value of secant x. So this is going to be natural log absolute value secant u. And that's step 3. We just did the new integral. And then step 4 is to substitute back to get x's instead of u's. So I'm just going to replace u with 3x plus 1. Okay. Now let me go over, and this is something that I've tried to mention a few times in class, but I'm going to go over it again because we just saw an example of it. let's say there's an antiderivative that I know. Like, let's imagine that this is something on my list. Like, this is just, say, the antiderivative of cosine is sine, or something like that. We're just imagining that these are two functions on the list. And then what you have to do is something slightly different. Instead of doing the antiderivative of f of x, you're doing the antiderivative of f of ax plus b. There's a shortcut to do this. I'm going to go ahead and show all the work right now because we're doing u substitutions. Well, what would I want to do? Standard advice is to let u be the inside of a composite function. So I'm going to let u be the inside here. Du is, and let's keep in mind, a and b are just numbers, like 2 and 3 or something. The derivative of this with respect to x is then just, well, the b is a constant, so that disappears. The derivative of a number times x is just that number, so this derivative is just a. And then I'm supposed to write dx. And then I'm going to take this integral, and this is where I start step 2. I want to complete the substitution. Obviously, I made this u for a reason, so this is f of u. And then the dx is still not accounted for, but I can do the standard trick. I can solve for dx here. It's 1 over a du. Right? And now I say, well, the 1 over a is just a number that I can pull out. And then what's the antiderivative of f of u? Well, we said the antiderivative of lowercase f was capital F. So that's just what we're doing. So this is capital F of u plus a constant. And then finally we go back to x's. U, if you recall, was ax plus b. And that's always what you get. Just to remind you, that's like the example that we just did. This is like, we know this one. This one is on our list. The antiderivative of tan x is natural log absolute value secant x plus c. But we weren't doing the antiderivative of tangent x. We were doing the antiderivative of tangent 3x plus 1. So that's like this down here, 3x plus 1, so it's like a was 3 and b was 1. And then look how similar the answer is. The antiderivative of tangent is natural log absolute value secant x. The antiderivative of tangent 3x plus 1 was, it looks like the same function. I see a natural log of an absolute value of secant. The same thing is here and here. And what do I have in front? I have 1 over a, just like this, because a was 3. So that's where this 1/3 comes from. So I'm not going to mind if you go through the work every single time. If you have this example to do, I don't mind if you go through the work of really showing the work of the u substitution to get what you get. But it is possible, and I encourage you to try, it is possible to knock these out in one step. I'm going to do the next one like that. What I notice about the next one, I see e to some power. And I know there's something on my list, antiderivative of e to the x dx is e to the x plus c. But I'm not doing the antiderivative of e to the x. I'm doing the antiderivative of e to the 2x minus 3. So what's this going to look like? I take this function that's the antiderivative, and of course we're doing e to the x, so the antiderivative is the same as the original function. I'm going to put the same thing inside, and I'm going to have 1 over the coefficient of x. That's this 1 over a. So I'm going to have a 1/2. And that's it. You can really just do this in one step. I am completely fine if you do this in one step without showing any work. Yeah. So let's do another one. Okay, so I'm doing 2 more examples, and I'm saving the interesting ones for last, and then the last 2 I consider at least slightly interesting. So let's try these together. I've got this integral. Just as a first shot, I'm going to try what I would call the standard advice. The standard advice is to let u be the inside of something. I see a square root and then this guy underneath the square root. So I'm going to call this is like the inside of the square root. That seems to be a good candidate for u. So I've determined what to make u. Let me go to complete the substitution. And I know that completing the substitution always involves du. So this is easy enough. The derivative is just 2, and then I'm going to write dx. Okay, so here I go. I want to complete the substitution. I don't like the letter x. I want to replace everything with u's. So there's one thing that's obvious, which is that I can just call this the square root of u now. And as I often do, I've skipped over something. I'm not quite sure what I'm going to do with this x. Maybe I'll decide later, but I'm just going to remember that there's something to do there still. Regarding the dx, I can do what we've done a few times, which is just take this and solve for dx. 1/2 du. And then I really don't know what to do about this x. Well, I know, but I'm pretending that I don't know yet. Let's pretend that we're all confused together. This is what I was describing a minute ago as one of these awkward intermediate steps where I have both x's and u's, and of course I'm not done completing the substitution if there's any x's left. So I'm not done. I've made some progress, but there's still that one x to go. And if you remember, we had one example like this. This is just the second example that I did in this video. And we arrived at this intermediate step, but at that time, we had something sort of miraculous happen, which is I had x's in this step, but then they just canceled and there was no more x's. And that was great. Unfortunately, we are not so lucky this time. I don't see a 1 over x to cancel this x. So what am I going to do? One thing you can do is if you're in a situation like this, you can go back to the equation when you determined u. You can solve that for x. I'm going to solve this for x, and then whatever I get, I'm going to put here. And then there won't be any more of the letter x involved. So this is easy enough. I'm going to subtract 1 and divide by 2, so hopefully it's okay if I just do this in one step. X would be u minus 1 over 2. Okay, so I would call this the end of step 2. The substitution is complete because I don't see the letter x anymore. I only see the letter u. Step 3 is that I have to do the new integral, and maybe this is starting to make me a little bit nervous again. This isn't a pretty thing. You know, often in the previous examples, as soon as I was done with step 2 and I was moving on to step 3, I said, oh, look, it just turns out that we have something that's on our list and we remember what it is. This isn't something on my list. However, it's not that bad. So what do we have here? I've got some constants. I've got a 2 in the denominator and basically another 2 in the denominator from this. So those don't bother me at all. I'm just going to call that a 1/4, and I can pull that all the way out. Now let me, what I have other than that is just, I would call them powers of u. I mean, this is like u to the 1. This is like u to the 1/2. And powers aren't really a big deal when it comes to finding antiderivatives. Let me just be a little careful about it. I want to do a little bit of algebra here to multiply this out, because when I distribute this, these are going to end up being different powers. So this is u, because this is u to the 1, right? So I end up with u to the 3/2 minus u to the 1/2 when I distribute that. And now I'm just using the, now I would say officially this has boiled down to things that are on the list. I know how to do the antiderivative of a power of u. What I do is I increase the power by 1. It's now 5/2. And, oops, okay. Sorry, I'm getting a little bit ahead of myself. Let me put a big set of brackets here, because I want to remember, I'm about to have multiple things inside these brackets, and I just want to remember that this 1/4 gets distributed to everything. Now let me go back to what I was saying. I was writing down the antiderivative of u to the 3/2, and I increased the power by 1, so that's 5/2, and then in front I'm going to write the reciprocal of the new power. The reciprocal of 5/2 is 2/5. Let me do the next one. I increase the power by 1, that's 3/2, and then in front I write the reciprocal of the new power, that's 2/3. Okay. Last step is I want to go back to x's. So, let me write. So u was 2x plus 1, so I'm just going to replace that. I'm also, hope you don't mind, I'm just going to clean this up a little bit and distribute the 1/4 and simplify the fractions a bit. 1/4 times 2/5, I can cancel a 2 and I get 1/10. So that's just taking care of these fractions. Other than that, I've got u to the 5/2, which is 2x plus 1 to the 5/2. What else do I have? Well, 1/4 times 2/3, a 2 cancels and I get 1/6. And then u to the 3/2, that's 2x plus 1 to the 3/2. And then I remember my constant. And that's it. So, right, let me just, I left a little bit of space underneath step 2 to talk about it. when you're completing the substitution, of course, the first thing we always do is we find du, and maybe we solve for dx. This is something that we've often done. Du is going to be whatever the derivative of u is, and then I write a dx there, and then the next thing I'm going to want to do is I'm going to want to replace dx because I'm trying to complete the substitution, and what you can always do is just solve for dx. Also down here, this is something that just came up, is we ended up here in this step where there were both x's and u's, and we couldn't find a way to cancel the x. And what saved us in the end is we looked back at our original substitution and discovered that we can just solve that for x and replace the x's with whatever we get from solving for x. So I'm just going to write down here, let me put the word maybe. Maybe solve for x. Okay. One more for this video. Yeah, so maybe I won't say too much about this before I give it a shot. Let's just go with what would seem to be the standard advice. I see what I would consider a composite function. I see e to this power, and this is all up in the power. Like x plus e to the x is all in the power, and I'm raising e to all of that. It looks weird, right? There's an exponent inside of an exponent, but it is what it is. And I would consider this a composite function where this is the inside. So let's try u equals x plus e to the x. Du would be 1 plus e to the x dx. And then, yeah, so this integral, I'm going to start trying to complete the substitution. Part of it seems obvious. The whole point of making this u is so I can write e to the u. And then, well, I've got this dx, but maybe that doesn't worry me yet, because I can always just solve this for dx. Dx is du over 1 plus e to the x. Okay, and at least everything's accounted for, because this part was the e to the u, and the dx got replaced with this. So everything up here is accounted for, but I wouldn't say my substitution is complete yet, because this still involves both u's and x's. And again, I don't quite see a way, like I don't see a 1 plus e to the x to cancel with this 1 plus e to the x or anything like that. Well, I can try what we tried last time, which is, if you remember, I can go back to the original substitution and try to do some algebra there. I can't really solve this for x. Let me try some stuff here. I mean, I can move the e to the x over. So x is u minus e to the x. But that's not really solving for x because I have x on both sides. I could do something else, like I could take this and then say, so e to the x is u minus x, like I just got the x over. But that's not really going to help either. I mean, I can write down what I would get, but I'm not really making any progress, right? All I'm going to do is I'm going to replace e to the x with u minus x. And the problem is I still have x's in here. And now I'm kind of stuck. So, and this is why I'm not doing this example to scare anybody, but math is hard sometimes, and it's hard to give people advice that's like gonna work all the time. If you remember when I was giving you advice for what's a good idea to make you, I mentioned, and I'm emphasizing this now, I mentioned that it's not really possible to give you advice that's going to work in all situations. We followed this advice, and we are thoroughly stuck. And it's not that I'm going to find any way to fix this. This is just, as it turns out, this isn't a very good idea for what to make you. So we made a mistake together, and that can be a good thing, because we can learn from mistakes. I'm going to do something, I'm just going to do some real easy algebra to this integral and then approach it from a different angle. As we know, addition in the exponent can turn into multiplication. So if I've got e to this plus this, that can turn into e to this times e to this. So it's e to the x times e to the x. And that's just algebra. Now I'm going to follow the standard advice, but from this point of view. From this point of view, I see a composite function. I see e to the x, and I'm going to let u be the inside of a composite function. Now let me go to try to complete the substitution now. Of course, this is going to involve du. Of course, the derivative of e to the x is just e to the x. And now everything is just like magic. Of course, well, yeah, so this e to the x, that's u. This e to the x, that's e to the u. This dx, I can do the thing I usually do, which is just solve for dx. Like that. And then, yeah, actually, maybe I made this sound a little bit easier than it is. I said it was like magic, but I'm still in a little bit of trouble here because I still have both, I have both u's and x's. Like I've got this x down here, and I would like to find something to do with it. But actually, this isn't really that hard. E to the x was u, so I can just write u down here. In fact, that just cancels this one. So in the end, I just have the antiderivative of e to the u, which is e to the u. And then finally, I go back to the variable x. So I'm going to replace u with e to the x. So the final answer is e to the x plus c. All right. So finally, let me leave you with some advice. Why would you use U substitution? Because we just went through a bunch of examples, and of course this video is all about U substitution, so we used U substitution every single time, but you're going to have examples where maybe it's not clear whether you should use U substitution, and then how do you decide? First of all, if you see a composite function or a fraction, remember the standard advice for U substitution is to make it the inside of a composite function or the denominator of a fraction. In other words, if you see something involving e to the sine x, it might be a good idea to let u be sine x. If you see the square root of natural log x, it might be a good idea to let u be natural log x. If you see this kind of fraction, it might be a good idea to let u be the denominator of the fraction. And if you see these kinds of things, it might be a good idea to do a U substitution. A second reason is, and if you get experience with U substitutions, you'll get good at looking a step ahead. And completing the substitution always involves replacing the du. And whatever you make u, du is going to be the derivative of that. And you can start thinking to where you can see one step ahead and already see what happens with the du. For example, if I see one like this, of course, I see a composite function. My brain immediately starts to think, what if I made u equal to sine? If u was equal to sine, du would have a cosine. And so when I see these two things together, it's like I already know it's going to work out. Similarly here, if I see the square root of natural log x, I'm tempted to make u the natural log of x because it's the inside of a composite function. And if I did that, then du, if u is natural log x, du is going to have a 1 over x. And I like that because I see the x in the denominator. So you can start to think one step ahead before you even write anything down to show the work. You can sort of see that it's going to work out for you. Of course, in general, like I said, I can't give you advice that's going to work all the time. So another perfectly fine reason to use U substitution is just because you're in the mood, because you feel like it, you're curious to see what's going to happen. Anyway, I'll stop the video here.